discussion on fault tolerance, but just as an aside, I'll again repeat the same thing I sent by email. The midterm is going to cover lectures 1 through 15, chapters 1 through 6. All the lecture notes have also been posted. Everything is up to date. Okay, so again, if you have questions, ask me or the team. Right, so let's continue our discussion on fault tolerance. This is not material for the midterm, but certainly final. Attention. Okay, so it's going to be part of the final exam. So we started talking about fault tolerance towards the end of last class, and we basically said in distributed systems where there are lots of machines, lots of software components, the probability of any component failing or going down starts approaching 1 as the number of components starts approaching infinity. So you have to design your systems assuming that failures are the common case. Okay, typically most systems assume that failures are the exception. Normal operation is the common case where no components are failed. In distributed system is exactly the opposite, especially large distributed system. If you have one client and one server, you can still assume that failures are not the common case. But if you have 1,000 servers or 1,000 components, then you have to make different assumptions. You have to design your system differently. Okay, so using fault tolerance principles are actually at the heart of some sort of design principles. So what we will do today is to look at some high-level ideas on how you can deal with faults. Okay, and we will look at different kinds of faults and see how one can go about designing systems that will allow us to deal with these faults. And this material follows nicely from the material on replication. Okay, because we talk in replication chapter, we mostly talked about consistency, the problem of consistency. But I had said that you can also replicate for high availability. So if some machines go down, other machines are still running and they can take over or they can continue their task. Here we are going to look at how do you actually use replication to ensure you can tolerate faults of any sort. Okay, so that's basically the connection or the reason we have the sequence. So we are going to talk a little bit about agreement in the presence of faults, and we will talk about reliable communication, and maybe we'll get through a little bit of the distributed commit part. Failure recovery we may or may not get to today. Okay, just there in the lecture slides, but we may have to look at it next time. Okay. So to understand how to deal with faults and how to use replication, let's take first a very simple circuit that is actually shown. This is a hardware circuit, not a sort of a hardware circuit that has 3 components, A, B and C. Okay? So the input comes to A does something to the input. Here this one line means 1 bit input. Okay? So there's 1 bit that is going to come in. Okay? A is going to do some computation. It is going to produce a 1 bit output that goes to component B and that goes to component C. So what is on the top is a circuit with no redundancy, there is no replication. So if any component A, B or C becomes faulty, the circuit will stop functioning. Okay? So what is shown at the bottom is a replicated version of the circuit which is designed to handle a fault in any component A, B or C. Okay? And the way you do this is you basically have multiple copies of the same circuit on the hardware. Okay? The input is replicated and fed to all of those copies, and then you are basically going to see what output is produced and somehow deal with that output and figure out what to do in case of a fault. Okay? Here we have 3 copies of every hardware component. So A has A1, A2, A3 is rather than 1 copy of this circuit B. You have B1, B2, B3, C1, C2, C3 and so on. Okay? And this figure that is shown here is referred to as triple modular redundancy because there is 3 copies of everything. So there is 3 copies, so it's called TMR. Okay? And the idea is very simple. The input is fed to every stage. You take the output of every stage and you vote. Okay? This circuit is designed to handle 1 fault. Okay? So 1 copy of A1, A2, A3. This is the same circuit, 3 copies of it, but any one of these could be faulty. Okay? So the assumption is if one of it is faulty, it will produce the wrong output, but the other 2 are functioning right. So if you vote and take the majority, you will have the right output. Okay, so you produce an input and A1 says you do the computation and the result is 0, and A2 and A3 say the result is 1. Okay? And then you know that A1 is faulty because A2 and A3 agree, but A1 doesn't agree. And if you are designed to handle 1 fault, then you can basically take the output of the majority and say that is the output of the circuit A. Okay. And so this is what the voter stage is doing here. Okay. So the voter is simply basically a comparator, okay, that takes the majority. Okay. That's a hardware circuit called a comparator. It's going to basically take the output of each of these three and then say what, just take basically if they all agree, then there is nothing to do. Okay, you just pass that. If they disagree, you see which two are in agreement and then you take that and you pass that on. Okay? Is that clear? So you can ask, why do you need three of the voters rather than one? Basically you could just have one voting stage and have that compare and then produce an output.
Lossy channels? You can have lossy channels?
Okay, you could have lossy channels. That's one observation. Any other thoughts here?
The voters also, if they are also not functioning right.
Okay. So there is nothing that we said that the voter can never have a fault. Okay, this is just a hardware circuit. Any component can fail. So you replicated these components, but and then if you have only one voter, and what if that voter is faulty? And it basically compares, but it produces the wrong output. Then the circuit will still not function. Right? So basically then what you do is you have three voters that do the same thing. Okay, you have three voters here, each of them takes the output of the previous stage and says what is the right output. Okay, what's the correct output. So even if one voter is faulty, and you can see that each voter is only feeding one component in the next stage. So if any of the voters is faulty, right, it will only send a wrong input to the next stage, but then the other two voters are assumed to be fine. Okay? So they will produce the right output, and at this stage, because B1 may receive the wrong input, even though B1 may not be faulty, it's receiving the wrong input, it will produce the wrong output, but B2 and B3 are okay. So this is basically how you are going to deal with it. So you cannot assume just because there are faults, only the main part of the circuit is faulty. Even voters may be faulty. So these are just hardware components, anything can fail. So you want to design it so that no matter which component fails, okay, your system is going to function correctly. Okay. Now this is a hardware circuit. Now this will be clear shortly why we talked about this notion. I mean, the important thing here is a principle which says the right way to handle, not the right, but one way to handle faults is to have redundant copies of the component, whether it's hardware or software, it doesn't matter. Okay, and then have them produce output and vote. Okay, and then the vote, basically the output of the voting will tell you what the right output is. So if some components are faulty, okay, they'll produce wrong results, but then you vote on the results and see what is the right result of these components. So we are going to use the same exact principle, although this is meant for hardware design. We are going to use the same exact principle to design reliable software that is faulty and is going to produce bad output. Okay? Is that clear? So basically the crux of the problem is how do you design these voters and how in a more general way than what I just talked about, and what do they actually do in software. Okay, that was a very simple one-bit example, but in reality you may have three copies of the database, you run a query produces results, what is the voter to do, how does it work, and so on. Okay, the broad principle is the same, but we need to understand how they actually work. Okay? So we will assume we want to design a K fault tolerant system, which means that the system should be able to tolerate K simultaneous faults. Okay? Previous example here was one fault tolerant. We could handle one fault. Okay? But we want a general principle that says, I want to design a system that can handle K faults. Okay, K could be 1, 2, 3, any number. You specify as a designer K. And then the technique is going to tell you how many replicas to use, how many voters to use, how do they all work, and so on. Okay? So we want to make our system K fault tolerant. Typically for most practical system, K equals 1 is good enough. If you want to tolerate one fault, somebody else takes over, but you can have K simultaneous. Okay? So that's the first specification. The second one is what kind of faults do you want to tolerate. Okay? So the simplest kind of fault, as I talked about last time, is crashes. Okay? Basically the software crashes and it doesn't produce any output at all. A machine goes down. That's a type of a fault. Okay, so if you send it any input, if the machine is down, it's not going to produce an output at all. Okay, so you can ask, if that's the kind of fault you want to tolerate, then how do you design the system? Okay, what kind of replication are you going to put? That clear? What? Yes.
You need to have one more that the signal is going to work, so that even if everybody else knows, well, at least I'm going to correct that.
Right. So since we said the only kind of fault you want to tolerate is crash. Okay, so if one machine crashes, then you need a second replica if you want to tolerate one crash, one fault. Right? So essentially the principle is you need k plus 1 replicas to tolerate k faults, because the fault is a crash. Right? So if the machine crashes, it doesn't produce any output. So you need at least one machine to be functional to tolerate k faults. So you need k plus 1 replicas. Okay, so the only kind of faults that you want to tolerate are crash fault tolerance, then you don't need a voter here, because we are not assuming that you will produce bad results. The only kind of faults we are tolerating is produces no results. So if the result is produced, we are assuming that the result can be trusted and it's not faulty. So in that very simple case, you don't need a voter at all. You just need k plus 1 replicas to tolerate k faults. Okay? Very straightforward. So if k equals 1, you need 2 replicas. K plus 1 equals 2. So basically one crashes, the other one is going to tell you what the result should be. Okay? So that's a simple kind of fault. But in most cases, for systems don't just crash. They actually can have bugs. They'll produce bad results, not just stop functioning. Okay? So these are more sort of complicated kinds of faults to handle. Okay? So you may have your system will produce erroneous results, it will produce random results, it will produce malicious results. Okay? And you want to tolerate any of these kinds of faults. Okay? These class of faults are referred to as Byzantine faults. Okay? They are called Byzantine failures. So Byzantine essentially means that the system, any replica can do any arbitrary malicious things. Okay? Every once in a while it may seem like it's functioning perfectly well, it's producing the right result. Once in a while it's going to just produce some garbage. Sometimes it may fail to produce any result. It can do anything. Okay? And you still want to have a system where you basically can decide what the right result is. Okay? Byzantine faults are the hardest kinds of faults to tolerate. Okay? Crash faults are the simplest kinds of faults to tolerate. So these are two ends of a spectrum. There are things in between as well, but we are going to ignore them all. Okay, so we are going to just go, this one we said we just have k plus 1, now we'll see what we need to do here. Okay, so these are the most kind of notorious faults to tolerate. And this is where we are going to use voting. Okay, in the previous case we didn't need to use voting. So we'll assume that you have replicas, some number of replicas, they can be Byzantine fault. They can do arbitrary things. Okay? And you want voters to basically figure out. Okay? And because the system is Byzantine faulty, you have to assume that the voter can also be Byzantine faulty. Okay, voters can also have the same kinds of Byzantine faults. Just as in the previous case we said the voter can also have a fault, the same is true. Okay, any component in the system can experience a Byzantine fault. So we can't assume that the voter is more trusted than the components that are doing the computation. Okay, any part of the system can have Byzantine faults, and we still want to be able to decide what the right result is. Okay? So the question is, how do you do this? So when I say we want to decide what the right result is, you have to understand what we means. Okay, we could be an external observer, or we could be the software processes themselves that decide and produce an output. Okay, in this case we are referring to, you have a collection of processes and you say give me one output at the end of it. Okay, and then you basically, and all of these processes need to also agree on what the right result is. They will run this protocol. Okay, and then the voters there will vote and figure out what to do. So you want, basically this process is referred to as reaching agreement in faulty system. You want to vote and you want to agree that this is the right result, and you want all processes to also agree. Okay, the faulty processes will disagree. The majority should agree that this is the right result. Okay, and produce an output. Now this is a class of protocols. Okay, you may have heard of this term consensus. In distributed system, there's a class of protocols called consensus protocols. Reaching consensus basically also means reaching some agreement, saying in case of Byzantine faults, what can we do? Okay? So look, consensus protocols are basically also relate to the same type of scenario where you want to reach agreement. Okay, you will assume that your system may have Byzantine faults and you want to be able to deal with it. So we'll start with a very simple example and try to build from there. Okay? The simple example is we'll assume, okay, that there are two processes. Okay, no replicas right now. Okay, we'll keep voting is going to come on the next slide. This is a very simple example of what can happen if you have Byzantine faults. Okay? Let's assume that you have two processes that want to communicate with one another. The processes themselves are not faulty, but the network is faulty. Okay? They basically exchange messages, but the network is faulty. Okay? It may basically flip a bit, okay? Because it will corrupt the message you are sending. It's called flipping some bits, and then the wrong message arrives at the other end. For simplicity, we'll basically assume that you are just exchanging a 1-bit message. Okay? The message can either be 0 or 1. Okay? But the network is allowed to do arbitrary things. You send 0, sometimes network delivers 0. You send 1, sometimes network delivers 1. Sometimes it decides to flip. You don't know. Okay? Now the question is, can these two processes agree on what the message was? Can they reach agreement? Okay? And if so, what protocol should you use to figure out whether you received the right message? Okay, you need to reach agreement, and agreement basically says, I agree that this is a message, and I also know that you agree that that's a message. Agreement doesn't mean I received one, so I am happy with that message. Agreement means that I also know that you have agreed that that's the right message. That's what agreement means, right? So basically both parties have to agree, and each party needs to know that the other party has agreed. Okay, so how would you go about doing this? Because there is an analogy here. Okay, that's sort of a example from a distributed system, but here is the example that we will use to do the reasoning. And let's assume that there is an army that's split into two that wants to attack a common enemy. Okay? The army is split into two, so there are two generals. Okay, that's basically lead. They are part of the same army, but their army is split into two. Let's say they are attacking from two different ends or some such thing. Okay? And they want to agree to a plan on how to attack. And the only way they can agree on something is to actually exchange messages. So they'll send a messenger and say, this is the plan I want to propose, go and deliver that to the other guy, or the other general. The other general may send you messages also. Right? And you want to ensure that you actually reached agreement, which means that the general knows that the other party has received my message and that they also agree to the same plan. Okay? And we'll assume that for the messages, when the messenger goes from one point to another, they have to go through hostile territory. So anything can happen to the messenger. Messenger may get captured, and fake messenger from the enemy may actually go deliver a wrong message to the army. We do not know. Okay? But yet you need to be able to figure out that your message has been received successfully and so on and so on. How would you solve this problem? It's the exact same problem as two processes that are communicating over an unreliable channel.
So we need to make sure that there's a path between all of the good nodes or processes, such that the message does not go through any bad territory.
Okay, so one solution is you need to find a path that is going to not have the same problem, meaning that it doesn't go through any bad paths. Okay, so find solution if you have the luxury of having multiple paths. Okay, so the scenario was you have two entities and there are multiple paths. Okay? If you could find one that you know is not going to have any problem, so the message is delivered perfectly, you are good. Right? That's true. What if you did not have that luxury? You don't know that there is what path the messenger took. Okay, all you know is I know the other end can be trusted because he's a general I trust, and I want to send him a message, but with this is basically you have to go through some territory. You have no idea what can happen in that territory. There may be enemies or spies sitting there, and they may capture the guy, they may alter the message. Anything could happen. So you ask, what protocol would you use first? Okay, so I send off a messenger. How do I know the other end has received the message?
Could you use encryption to make sure that it doesn't get tampered with along the path?
Okay, you could use encryption, but right the moment, let's assume that you don't want to go to encryption. Okay, so you could, but we'll assume that without all of this encryption, can we come to some agreement? Okay? What's the simplest thing you can do if you send a message but you want to know whether the message was received? Yes. Okay, you will receive an acknowledgement. Okay. So I send a message, yes.
But then an enemy could just spoof the thing back.
Yes, fine. So let's we'll look at all this. So these are all problems we have to look at. So first general sends a message to the second general saying let's attack at 5 a.m. Okay, and he needs to make sure that the other guy has received the message. Okay. So you will say that you better bring back an acknowledgement saying got it, I agree. Okay. Maybe the messenger actually makes it to the other end without getting captured. Okay. And then he says, here is the message. The other guy says, yes, let's attack at 5. He's like, got it, I agree, and he sends the message back. And the messenger actually comes back, and the first general receives that acknowledgement, saying that you have received my message and you agree with it. Okay, are we done in this scenario? We have agreement on this. So I send a message, the other party sends a message saying I agree. Can we claim that the two parties have reached agreement? Yes.
So the first one has to send their acknowledgement that he has already got the acknowledgement from the second one.
Okay. So now the second guy, the second person has sent back an acknowledgement saying I agree. How does that person know that the acknowledgement was received? What if the messenger got captured in transit and the acknowledgement was never received? The messenger has made it fine, but the first person, the second party doesn't know that. Okay, so you can say, I'll send an acknowledgement to the acknowledgement saying, I heard that you agree, so I agree. Here is an acknowledgement saying I received your message. Okay, so you send the messenger back. Messenger goes, let's say nothing happens, he delivers or he or she delivers the message. You say, do we have agreement? Okay, you can recursively say the same thing, that message went, but how do I know the message actually made it to the other end? What if this act for the act got captured by that this thing, by the enemy, and then we have no agreement? Okay. So this process is never going to converge. Okay. In fact, there is a proof that says if you have two parties and an unreliable channel, you can never have agreement. Because you will basically say, how do I know that this last message has actually made it? Because only if I know that the last message has made it, do we basically know that there is some agreement. But the only way to know that is actually send an act saying that message was received, but then you have the same problem. Okay? So this is referred to also as the Byzantine general problem. Okay? Your generals, and there are just, in this case the channel is Byzantine. Okay, not the general. Next time around we'll make the generals Byzantine. Okay, the channel is the traitor, not. So it basically says that if the generals are trustworthy, but the communication medium is not trustworthy, you can, if you have two parties, you can never reach agreement. Okay, because you will always send acts. You send an act to the act, but then you have this problem where you never know whether the last sent message was received successfully without being altered. That's basically the only thing that is going to keep us from agreement. So this problem cannot be solved. Okay, it's impossible to solve. Okay, so we'll assume that that cannot be dealt with. So we're going to put it aside. Okay. So now we'll sort of change the problem a little bit. Okay. We'll assume that the network is not the problem at the moment. So we'll assume that there is no such problem, but you have to we'll assume that one of the generals is actually a traitor. Okay, one of the generals is actually a traitor and is faulty, or he or she is going to do the wrong thing. Okay. Now you may know that you, the general, is trustworthy, but you don't know which among the other n-1 generals is the traitor. Okay. You do not know. Okay. And yet you have to basically send all the other generals have to reach agreement that this is the plan to attack them. Okay. So now we will generalize this problem. Rather than army being split into two, the army is split into n groups. Each is commanded by a general. One of these n generals is faulty, Byzantine faulty. Okay. Byzantine faulty means he generally showed enough that he or she will not reveal that they are faulty, but they will do arbitrarily bad things. Okay. Sometimes they will look perfectly trustworthy and they will agree with everything you are doing, but then they may do something that is going to basically cause some problem. Okay, that's what Byzantine faulty processes do. Sometimes they appear to be functioning right, sometimes they do produce wrong results, they don't produce any result, they can do anything. The same is true here. Okay, so the kind of question is, can n generals with a perfect channel, in this case if we assume a message is sent, we will not assume that the network is doing anything, the message is actually received fine. Okay? This is the equivalent of saying I am going to encrypt the message and digitally sign it. So if the channel tries to tamper with it, I can detect that. Perfect. We have not done security or encryption, but there are techniques that say if the channel tries to alter it, we can detect tampering. But if the message itself is faulty, if the general actually sent a bad message trying to trick me, that I cannot detect because I don't know which general is actually the traitor. Okay, so we are trying to figure that out. Okay, so perfect channels, but one of the generals is a traitor. Okay, so how do you go about doing this? Okay, before I present any solutions, you can ask yourself the question. Okay, if you have, I'm going to make that simple, right? If you have n friends, n minus 1 friends, and you think that one of them is not to be trusted, but you don't know which one. How do you figure out which of your friends is person you shouldn't be trusting?
Send messages through all the friends. So instead of sending one message to all of them directly, send message to one friend and ask them to propagate it to the next person. So whenever a new friend gets that message from another friend, he should send you an acknowledgement. So that way you will know if someone has tampered with the message when you're getting an acknowledgement for that.
Okay. So you are saying you should send messages to a friend and have them forward messages, and then you will see if somebody tampered with it. Okay. So that's sort of the idea. But remember, we have to reach agreement here. The broader problem we are trying to think of is rather than the general, you have a replica of a software process. Let's say it's a database. Okay. So you have n databases. One of them is corrupt. Okay, you don't know which one. Okay, you send the same query to all data. You send the same request or same query to all the databases, and you want to figure out which one is Byzantine. Sometimes they all will agree. In this case, there is no problem. If the faulty guy does the right thing, there is nothing to do. You don't have to single that replica out. But if the faulty replica tries to produce some garbage, you want to detect it and figure out that is faulty. In the end, we are going to use the same voting idea. There is no other way. You ask everyone, and then you vote on what you have asked, but then you basically have to figure out who is producing the wrong results and sort of isolate that person, and the rest of them say this is the right thing to do. Okay, that's what you have to do here. You have to ask everyone what should we do, and then somehow figure out that if some traitor is producing the wrong results, everybody has to figure out that is the one that is producing garbage. Everyone else is actually agreeing, so this is the right thing to do. That's basically the idea of what we are going to do. Okay, but we are going to sort of use a protocol to do this. Okay, so we'll assume this is a Byzantine general problem with 4 generals. Okay, the nodes there are the 4 generals, and they are going to exchange some messages to figure out which node is faulty. Okay? And remember, the faulty node can do arbitrary things. It may behave like a correctly functioning node. Okay, in that case, there is nothing to do. We just need to agree on, if I send a request, what's the response? If I send a query, I want a response. The faulty database just happens to produce the right response, I have nothing to do. I still agree that this is the right response. Only when it does the wrong thing do I need to isolate it and discard its responses. Okay, or so ignore its response. So here is basically the Byzantine general problem. It's also an algorithm designed by Lamport. It's a person who can come up with logical blocks and Lec18. So we basically assume that there are 3 generals and 1 traitor. None of the generals knows who the traitor is except the traitor. And now you want to reach agreement. So we will basically have a multi-round process. In this case, we'll converge in 2 rounds. So basically, we'll say you start off by saying it doesn't matter what kind of problem you are trying to reach agreement in. Let us just assume that they are just exchanging how many troops each of them has, how many soldiers do you have, and you want to make sure that you are sending me the right information about how many soldiers you have. Okay? So in this case, we'll assume that each general announces his troop strengths, in terms of kilo soldiers. Okay, how many thousands of soldiers you have. Okay, we'll assume for simplicity they are numbered 1 through 4 and actually they have that many kilo soldiers just to simplify the problem. So general 1 has 1000 soldiers, 2 has 2000, 3 has 3000, but you know that 3 is the traitor because I marked it grey, but the soldiers, I mean, the generals don't know that. And 4 has 4000 soldiers. Okay, in round 1, each of them is going to broadcast their strength. Okay, so you're basically 1 is going to send a message saying I have 1000 soldiers to all of them. So you see a message going 1 to all. So 2 says the same thing. 3 can do arbitrary things. Okay? It can send a message X, Y, Z announcing 3 different numbers to 3 different soldiers, to 3 different generals. Okay? And X, Y, and Z could be anything. They could actually agree, they could disagree. We don't care at the moment. Okay? So that's why we just call them X, Y, and Z. Okay? So at the end of the first round, after you're done this, General 1 has gotten a message saying I have 1, I know that. 2 sent me a value of 2. 3 sent me X. Okay? X is to put any integer there, it doesn't matter. Okay? And 4 sent me 4. Okay? And then 2 is going to basically say 1, 2, Y, 4. This one, 3 knows its real strength. So it's going to get 1, 2, and it knows it has 3. And it got 4 from 4. And this got 1, 2, Z4. At this point, we don't have any agreement. We just have, each general has announced how many soldiers he or she has to everyone. Okay. Now to figure out who the traitor is, what we do is we ask each of the generals saying, tell me what you received from the others. Okay, so we want to see who is lying. Okay, so each person has told all the others saying what they have. And now you tell everybody is asking everyone else, tell me what you received from all the others. Okay, so basically each general now has to take this vector and send it, broadcast it to everyone else. Okay. So at the end of the second round, 1 is going to get 1, 2, Y4 from 2. Okay, that's this value. It's going to get A, B, C, D from 3 because 3 is a traitor. It can send whatever garbage it wants in the second. Could actually send the right values, it could send the wrong value. We want the protocol to be oblivious of what it is sending. Okay. And 3 is going to send 1, 2, Z4. 4 is going to send this value. Okay. And then same thing happens at 2 and 4. Okay. So now the question is, if you look at this, if I now have asked everyone and everyone told me what they received, can I figure out who's lying? Right, so in this case, 2 of the generals are actually agreeing on what they have sent to others and what they have received from the right one. But the third guy, which is this one, seems to basically have a sort of that number is mismatching. So you'll see that their column doesn't match, and when you ask them, that also doesn't match. Okay? So you can take the other 2 and say, I now know that this is lying. Now if it so happens that the 3 is being Byzantine and actually sends the right values, okay, they will actually match. But that's okay. If it matches, then in this case it's in a state where it's not faulty, so you can believe it. Okay? But it starts sending garbage, you can isolate it. Okay, so there is no way for 3 to trick you into believing that it is actually not faulty and yet it sends you garbage. If it is faulty, you will isolate it. If it's not, it's Byzantine but not acting faulty, you will basically, it will agree. All these protocols will converge and will get switched.
So what if 3 sends the right messages to 1 and 2, but sends the faulty messages to 4?
Yes. So you can ask what if 3 sends the right messages to 1 and 2 and say faulty messages to 4. If you send a faulty message to 4 in round 2, 4 is going to broadcast that back to everyone else. So you will basically have 2 entries matching here, but that doesn't match. These are arbitrary values. That's why you call them A, B, C. In this case, 2 entries will match, the third entry will not match. But then you know that 3 sent that value. Right? Because that's the column that's not matching. So you are still isolated it and you basically figure it out. Yes.
What if the traitor pretends to be the loyal generals? So it sends 1, 2, and 4 to all the other generals, but it lies on the number it has.
Yes, so we are assuming, yes, you are right. So question is, what if the traitor sends the right values 1, 2 and 4, but it lies about what you have. So if it lies about what it has, then basically this is exactly the column that will not match. right? Because what it has broadcast to everyone is not matching.
It could be consistent though, right? You could send the wrong values, but the same values to everyone.
Yes, that's okay. Right? So because let's think about this, rather than 1, 2 and 4, these are the output of a query. These are databases. You send a SQL query. Okay? And now 3 databases are producing the right results. Rather than a SQL query, let's say it's just a computation. You say add 2 and 3 and tell me the result. Okay? So one says that 2 plus 3 equals 5, that says 2 plus 3 equals 5, this says 2 plus 3 equals 4, that says 2 plus 3 equals 5. Okay, now if this is producing the wrong result, then you will basically have a mismatch in that entry. All these other values will actually match. Okay, so we are just basically sending a different kind of message, but in reality you are going to send the same computation, the same request to all the replica. You will expect that the results will actually match. Okay. So the idea is very simple. You basically send the request, everybody produces responses and send it to everyone else. Then you ask what did all the others tell you, and you tell that to everyone else. And at that point, if somebody is lying, they will be caught, because at least the other 2 are not lying, so they will take the lie and propagate it back to everyone else. So you know that person. Okay. So that's the idea. Now you can ask the same question with. You are trying to do the same protocol with 3 generals, not 2. Okay, and see if you can come to some agreement. Okay, in this case, you will actually see that you cannot agree because there is no majority. And the way to, I'm not going to go into the details of this, but I'll try to explain this with an example. Okay? Let us assume that you have 2 friends, okay, and one of them is not to be trusted. One of them is lying, one of them is telling the truth. Okay? Now, if you ask them the same question and they give you 2 different responses, okay, to that question, you have no way to figure out who is telling the truth and who is lying. Okay, if you don't know. Okay? Same is true if you have 3 generals. Okay? One knows that it is trustworthy, but it doesn't know whether to trust 2 or 3. Right? So that's you. One is you. These are the 2 friends. You know one of them is a traitor. You know you are not a traitor. You are telling the truth. You know one of these other 2 is lying, but you don't know which one, because they are just disagreeing. They are just giving you 2 different results to the same question, but you cannot figure out which of those 2 to pick. Is that clear what I said? The broad intuition. So what this is basically saying is the same problem as the previous one, but it's saying that if you have two loyal generals and 1 traitor, each loyal general cannot figure out which of the other 2 is the traitor. You need a majority essentially. So if you are the observer and you are observing the rest and they are disagreeing, you can't figure out what the right answer is. In the previous case, if one of them is the observer, okay, there is a majority among the other 2. Those 2 are actually agreeing and disagreeing with this one. So this general can figure out that those 2 are telling the truth because they agree and they disagree with this. Similarly, one knows that 2 and 4 are agreeing and they are sort of in disagreement with 3. So you can actually isolate the party that is faulty. But if you basically take that down from 4 to 3, if you are the observer and you are trying to come up with some agreement, you cannot figure out what to do. Neither can you convince someone else what the right answer is. Okay? Is that clear? So what this is essentially saying is that if you have m faulty processes, okay, agreement is possible only if you have 2 plus 2m plus 1 correct processes out of 3m plus 1. In case m is equal to 1, that says in one faulty process, you need 3 out of 4 correctly functioning processes, okay, to reach agreement. In this case, that means if there are only 3, that condition is not satisfied. Okay. So basically, what that's also saying is you need 2/3 majority to function correctly. Okay, in your Byzantine fault. Now you have to distinguish between detecting a fault and reaching agreement. Okay. In this case, it is sufficient to have 3 processes and one can know that there is a fault because 2 and 3 are disagreeing. You know there is a faulty process because there is disagreement. they are producing incorrect responses. That's just detecting a fault. To detect a fault, this is good enough. To reach agreement saying what's the right answer, you need to add one more entity here which is functioning correctly, so that those 2 out of 3 will basically tell you the right answer. Okay, so there is a difference between detecting a fault and reaching agreement. Detecting fault is easier. You just have disagreement, you basically know that one of them is fault. You don't need to know which one. This is like you have 2 copies of the database. You send it a query, they produce 2 different responses. You know something is wrong because you send the same query, they produce 2 different answers. You don't know which one to take. Right? You will need one more replica to figure out which one to take. If only one is faulty, because you send the same query to 3, 2 of them will agree. Only the faulty one will disagree. Then you know what's the right answer as well. You all know that there is a fault and you know what's the right solution. Okay, so there is a difference here. So basically that's what they say. Detecting a fault is easier. You just need 2k plus 1 to detect k fault. Now in k is 1, you basically need 3. But if you need to have agreement, then you basically need more. You need 2/3 majority.
Why in the last example, like in the one got case, why one didn't use its own values? Like it got 1 to y and its own values were 1 to x.
Yes, good question. So here question is, why couldn't one knew it was trustworthy, why couldn't one use its own value and figure out that it is what the right answer is? Okay? This is the same problem as whether you know what to do versus you know everybody knows what to do. This was the problem of reaching agreement or reaching consensus. If one could use its own value and say, I agree with 2, so I know this is the right answer. Okay? But reaching agreement is not knowing what the right thing is, also making sure that everybody else also agrees with you. This was the same thing where we had 2 processes and a faulty channel. Right? So I sent a message, I got back a response saying let's attack at 5. So I know that that guy has received the message, so should I be happy? You have to also ensure that that person also agrees with you. Right? So in this case, one has figured out what the thing is, but how does it know that 2 has agreed with? That I think to do that you need one more process. Okay, so it's a little bit subtle point, but it's a good point. Okay, it's one thing to say I use my own solution, I use my own result and compare it with 2 and I know 3 is faulty. But can I convince 2 that 3 is faulty and reach agreement? That's the problem. Okay, so all you have done is you have basically figured out you cannot reach agreement. That's the point. The consensus is harder than just detecting faults. Okay, is that clear? So there are some certain things that you have to deal with when you do Byzantine faults, and this was one of them. Okay. Now you can ask the question, what does this mean for real systems? Okay. So it says that you need 3k plus 1 processes to detect Byzantine and faults and agree on it. So that means to detect one fault you need 4 replicas. Okay. K plus k equals 1. That's 4 replicas to detect one fault. And basically this solution. Okay. That basically says, and remember, crash fault tolerant, very simple. Detect k fault, you need k plus 1. So to one machine crashes, you need 1 more. So you just need to double your investment. Here we are saying to do Byzantine faults, you have to quadruple your investment. That's very expensive. You say, okay, one process can go haywire and do bad things. Now I have to quadruple, invest 4 times as much, and then all will be fine. Okay, in real practice, in real system, that's a very high price to pay to detect just one fault. Okay. So as a result, although there has been a lot of work in how to do Byzantine fault, practical systems basically cannot, in most cases the choice is that we don't have to deal with that, or we will not worry about dealing with Byzantine faults because it's way too expensive in practice. Okay. It's not that it cannot be done, it's too expensive. Okay. Rather than buying one machine and spending $10,000, I have to spend $40,000 to do the same thing. That's way too much. Right? From a practical standpoint. If you want to deal with Byzantine fault, that's the only solution. So most real systems may not be engineered to deal with Byzantine fault. They can deal with crashes just fine. Okay? Machine crashes, another machine seamlessly takes over. Okay? Machine has bugs and is producing garbage, that's a completely different problem. Okay? That will get exposed to users. You will actually see sometimes you send a request and something bad comes back. You have no idea what happened. Yeah, that's an example of a Byzantine fault. And in most cases, because of the high expense, no other reason other than the high expense, This is typically not done. Okay. But if you want to pay the price, that's how you would have to actually do it. Where all these generals were actually traitors or backstabbers. So nobody knew whom to trust and whom not to trust. So they had to go through some arcane processes to figure out how, if I want to simply agree with someone else, but I cannot even trust that person because anybody can come and do anything to you. How do you actually reach agreement? That's where this problem has actually come from. Okay. So this is, I'm going to skip this reaching agreement. I already said enough about it. Instead, I'm going to talk a little bit about reliable one-to-one communication, and then we'll talk about distributed commit and two-phase commit and things like that, which are actually used in practice. Byzantine fault tolerance, well studied, but too expensive to use. So it's good to know, but in most practical systems, you won't see anything like that implemented. Okay. So let's go back to one-to-one communication. So we talked about processes being faulty. Okay, now let's see what happens when you deal with network faults. Okay. In this case, again, there are multiple scenarios. Okay. The network can simply drop your message. That's like crash fault tolerance. The message you send a packet is not delivered. Packet just disappears. Okay. Or you can have a scenario you send a packet and some other packet appears at you. Okay. The network actually alters the packet and produces something else. Okay. So we are only going to again deal with the first problem, which is you send a packet, packet doesn't disappear. Okay, that's a far more common case where the router gets overloaded or something happens and the packet is simply discarded. Okay, having the network make Byzantine changes to your message. You send an email saying, yes, I will meet you, and the email shows up saying, no, I will not meet you at the other end. Most systems are not dealt to handle it. Okay. But we'll ignore that for the moment. We'll just look at the more common case of packet simply getting lost. So that is simply dealt with this whole notion of sending acknowledgements. So this is how TCP deals with packet losses. You send a packet, if it doesn't get there at the other end, you don't get an acknowledgement. So you wait for a while, if no acknowledgement comes, you resend. And you keep sending. If the fault is transient, eventually one of the retransmits will get there. If the network is actually gone down and is partitioned, then you keep trying and the message will never get there, but there's nothing you can do. If the network is partitioned, not much you can do. Only if there was some transient fault and the router got overloaded, sending a retransmit will actually help you. But this is how TCP is built. You send packets, wait for acknowledgements, okay? And then if acknowledgement don't come, you time out and you retransmit. And then hopefully after a few retransmits, some acknowledgement comes back, so you're succeeded. You move on to the next packet. Okay? So that's simply basically how you deal with this. Okay, the problem of RPCs and failures we already looked at. Okay, when I talked about extermination and so on, I said what happens when the server goes down, client goes down. So I'm not going to go into how these failures are dealt with at the RPC level. We'll simply look at how packet losses are dealt with at the network level. Okay. So it's very straightforward at the network level. You basically just send retransmits. Now there is a special case of how do you do this when you have multicast communication, one-to-many communication. Okay. So there's one sender, multiple receivers. Okay. You send a packet once, it's delivered to n recipients. Okay. Some fraction of those recipients may not get the message, okay, because the network simply dropped that copy of the message. So you could basically use a simple ACK-based scheme saying every time I send it, all the recipients have to reply to me. So I know that everybody received it. Okay, and if some of them don't reply to me, I'm going to resend it to them. Okay, so you could do this. So this is a simple ACK-based scheme. Okay, so you can do reliable multicast using simple ACKs. But the problem with simple ACKs is that the amount of processing the sender has to do keeps growing as the number of recipients increases. Okay, if you have 100 receivers, one sender, every packet generates 100 packets coming back to, 100 ACKs come back to. If I have 1,000 receivers, every message I send generates 1,000 messages back to. Okay, if there are 10,000, the same thing. Okay, so this doesn't scale. Okay, so now if you want reliable multicast and yet you don't want to make ACK processing to be a high burden on the sender, what can you do? That's really the problem you want to ask. Okay, is the problem clear? Okay, when network is dropping packets, you have a scenario of group communication, one sender, multiple recipient. could use the same simple ACK based idea. Say every time you send a message, wait for acknowledgement. If some parties don't send acknowledgement, retransmit. Okay, but the problem is now as the size of the group grows, the number of ACKs that are coming back also grows in the same proportion. And that makes it much higher burden on the receiver. Okay, so what would you do? It's a simple question and it has a simple solution. It's not very complicated.
So instead of sending many messages, many confirmations, you can just somehow centralize and send a single message saying that everyone has received.
Who will centralize it? So you are saying centralize, that's actually a technique that is used, but you have to think about who is going to do it. You could certainly come up with a complicated scheme where you have 4, so this one will send an acknowledgement here and you will basically send an acknowledgement back saying these 2 have received it and so on. And then you would have only one acknowledgement going on. So now, but everyone has to process multiple messages. Okay, so that is indeed a scheme that is used. It's called ACK suppression. If you actually have a tree-based delivery mechanism, this act works quite well. Where you have one sender and the recipients are sort of nodes in a tree. Okay, so you basically send a message, it just flows down a tree. ACKs come back, but then you take all the ACKs from your subtree and you send one ACK up. Okay, this technique is referred to as ACK suppression. This is also used simply to reduce the number of ACKs flowing back to the sender. Okay, but now the only disadvantage is every recipient has to do extra work to get ACKs and forward the ACKs. But that is actually used. It's called ACK based. Okay, that's basically it. Okay, so the solution really is to say, rather than acknowledging that I have received a message, why not flip it around and say, only tell me when you haven't received something. Okay, you must just send saying, resend this message, I did not receive it. Okay, this is referred to as a negative acknowledgement. Okay? This will only work in the scenario where you are sending a sequence of messages, not just one. Okay, you are sending a sequence, every message that you send is numbered. Okay, you have a sequence number that you increment. So you send the first message, you're saying message number packet 1. Send the second message saying packet 2. Send the third message saying packet 3. Okay? Now if you are receiving this sequence as a recipient, if you actually see a gap, you know that some message is missing. Okay, then you send a negative acknowledgement saying, I did not receive message number 24, I received 23 and then the next message that came was 25. So I'm missing 24, please send that back. Okay, yes.
And the last package lost.
So we'll come to the last packet problem. Okay, so if you have lost any packets in the sequence, you are going to basically, so that's what is shown here. So you get a negative acknowledgement called a NAC. Okay, this is a NAC based scheme. So here you only get a message. The sender only has to process genuine messages where it has to actually do something. You get a NAC saying send this packet back, you will send it. Okay, if the message was received fine, nobody says anything. I only tell you that I only complain when something goes wrong. I don't keep saying yes, got it, then that seems to be generating too much work. Okay. As was pointed out, the only issue here is when you send the last packet in the sequence. If you have to send 100, all 100 were 90, first 99 were received, but some recipients don't get the 100th packet. There is no 101st packet coming back to tell you that you lost a packet. Okay, so in this case, you might have to send a dummy packet saying end, this has ended. Okay, or you may have to just have to time out and say I haven't received a packet anymore. The last packet you have to come up with some heuristic to deal with. Yeah, otherwise the rest of it is easily handled using nuts. Okay. So that is basically how you will deal with the network. So we studied Byzantine general problem of what happens to deal when you deal with faulty replicas. I said what do you do when you have faulty networks. Okay, we haven't said what do you do if the network alters your packet. We only looked at the case where the network drops your packet size and doesn't deliver. Yes.
But don't we have the same issue where the back can drop? Because if we assume if no NAC comes back, everything's fine.
Yes.
The network can still mess up.
Right. So most of these protocols are actually built with some timeouts. It says that I send a NAC, I start a timer. If the packet I sent a NAC for doesn't come to me, I send another NAC. Right? Now the assumption is that all the packet drops are all transient. If there's an actual network fault, somebody went and cut the cable, for instance, which incidentally recently happened in Greece or so. Some divers went and cut an undersea cable and disconnected large parts of the country or from the internet. So you cannot send NACs and hopes for something to actually happen because the network has actually gotten partitioned. Only cases where there are temporary overloads or some routers are rebooting, some transient problem occurs, you can send NACs. Okay? So the assumption is if you send enough complaints, something will come back to you eventually. Okay? Any other questions? So that's one-to-many communication. We're going to spend maybe 10-15 minutes talking about this problem of atomic multicast and distributed commit, okay? Which is a slightly different problem. Yeah, again, it's a part of the discussion of fault tolerance, and reaching agreement, but there is a slightly different. So we want basically now to look at this problem of atomic multicast, which is I don't want to basically assume that I send a multicast message that some groups got it, or not some group, but some subset in the group got it and others did not. I want an abstraction from the system which says I send out a multicast message. It has to be all or nothing. So the system guarantees to me that everybody in the group received it, or if somebody did not receive it, then everybody discards it and nobody has got it. Okay, I want that abstraction. I don't want a scenario where some replicas got it and others did not get it, because that is problematic for it. Okay, so you can ask, why do you want such an abstraction? So here is an example of replicated database. Okay? Let's say bank database, okay, replicated on 3 different machines. You send a query saying go and add $10 of interest to this bank balance. I send it to all 3 replicas. And I want to guarantee that either all of them received that query. No, let's forget the execution for now. All of them received the query or nobody received the query. Okay, we don't want a case where 2 replicas have received the query and the network lost the third packet and it did not receive it. So 2 databases have executed this query and the third one has dropped it and is now out of sync. Okay, so it has to be all or nothing. If 2 out of 3 received it, then you basically tell the network, forget it. I'm going to retry because I don't want a case where the packet is only processed by some subset of the replicas. So this is a very common abstraction that you want for correctness reason. It has to be an all or nothing. You don't want something to be done by a subset in the group. Either everybody does it or nobody does it. And you want the system to give you this guarantee. So that's if you have a multicast protocol where the system or the network actually gives you that guarantee, or what is called atomic multicast. So the main problem here arises whenever there are faults. Okay, let's say one of the replicas goes down. Okay, packet cannot be delivered to the network. Okay, so in that case, everybody has to roll back and say, okay, that network, that replica has gone down. Now we basically isolate it and we become a new group, and then we basically throw out that message, and new messages are only sent to some other new group. Okay. So the question is, how do you deal with this issue? So there is this system called ISIS that was built as a nice case study in the textbook that basically uses this notion of a group U. So it says at any point in time, I know the group of replicas. In this case, there are processes P1, P2, P3, P4. At any point in time, I know the replicas that are up and running. And every time I send a message, the system is guaranteeing that all of them basically receive. And if at any point some process crashes, in this case there is a crash of P3, okay, the system has to detect it, notify all the group members of the group saying P3 has gone down. Okay, so any messages that were in transit while P3 went down have to be discarded because they cannot be delivered. Because you said all or nothing, in this case P3 went down while the message was being transmitted, so that's nothing case. Okay? So you discard that message, and then the rest of them agree that now that P3 has gone down, the new group is P1, P2, P4, okay, and then you sort of announce that this is the new group, okay, and then you isolated P3. So if the system needs to continue, then all subsequent messages will only go to P1, P2, P4, and there's agreement that that's the new group. or you can simply take the system down and try to get P3 back up and only then continue. What you do after a crash is detected and a new group has been formed is up to the application. If you don't want to continue because you want all the replicas to agree, then you will have to wait. But if you can continue, then you will continue, and when P3 comes up, you will run some explicit protocol to resynchronize it with the group. You have to run some special protocol so that it catches up and it's in sync, and then it can again be part of it. So this is basically referred to as atomic, or in this case is referred as virtually synchronous multicast. Okay, so basically the way you go about doing this is the middleware system is detecting whenever there is a crash, and that is referred to as a group view change. So that's just a term that is used there. And that the fact that some replica went down is broadcast to everybody else in the group. If they agree, then there is a new group formed. That is the old group minus the failed process. Okay, and then what happens at that point is up to the application. It can continue with that smaller group with the explicit knowledge that there is one replica down, and when that replica comes back up, you can resync it, or you can basically just wait and try to repair that replica and have it rejoin the group and then continue. Okay, but the system will not have lead you to a case where 3 of the 4 are continuing and you are not told and some bad things happen. So you are getting this atomicity problem. So now with that, so there's some example here which I'm going to skip. But with that background in mind, I want to talk a little bit about this notion of a distributed commit. Okay. So atomic multicast is actually an example of a more general problem. Okay. In that case, it was a multicast to all or nothing. Okay. This all or nothing property is actually needed in many different scenarios. Okay. So in reliable multicast, the operation of all or nothing or delivery of a message. So either a message is delivered to everyone or no one. Now we'll look at distributed transactions in just a second. Here the operation is everybody commits the transaction or nobody commits the transaction. Everybody aborts the transaction. So if you have a distributed database, you send the query to all parties and they execute the query. At the end point there is a commit step. It says, should we go ahead and commit? Once you commit, there is no going back. You are done. So just before you are about to commit, you better be sure that everybody is also ready to commit. Only then you go ahead. That way everyone is in sync. If any one party is not ready, then everybody rolls back, so you are still in the same. You don't want a case where some transactions actually commit on some replicas but not on others. Then you are in trouble because you are out of sync. So all databases will use this notion of distributed commit where you have to come to an agreement. This is again an agreement problem. Should we all go ahead and commit or not? If anyone disagrees, anyone can veto, and everybody rolls back. Saying it is safer not to commit because we will have disagreement. Okay, better to roll back because previously we are in agreement. Now if we disagree, then we are out of sync. Okay, but if everybody agrees, then you go ahead and commit. Question is, how do you reach that agreement? Okay, so this is a protocol we are going to look at. So this is the problem of distributed commits, and very similar to atomic multicast. This one we look in more detail. So it's all or nothing operation for a group of processes. We will actually look at this very classic protocol called 2PC, okay, two-phase commit. If you have taken any database class, you probably know what two-phase commit is all. Okay. So we'll now look at it. But this is, although it's used widely in databases, it's basically a general protocol that just allows a group of processes to agree. Here they are agreeing whether to commit a transaction. You could have used that to agree on anything. Okay, so this is what we are going to look at. This was it's a classic protocol designed originally or proposed originally by Jim Gray, 1978. So a very old protocol, almost 30 years old. Okay, so the idea is very straightforward. Once you understand it, I mean, it looks almost too straightforward. Okay, so what will we do? We'll have a coordinator. Okay. The coordinator is going to put this question to vote. Okay, so basically, these database replicas in this case have to agree whether to commit or not. Okay, we are going to basically ask every replica, what do you want to do? Commit or abort? Tell me yes or no. Okay, we'll collect the responses and we'll put it to vote. Okay, in this case, for safety reasons, if any replica votes no, that's like a veto. You're not going to do the majority and says 8 out of 9 said we should commit, so let's go ahead and commit. that won't work, because the ninth one may say, I don't want to commit because I have a local fault, something went wrong. Okay, you don't want the others to say, I'm going to override you because the majority have agreed. But that's not the point here. You want to be safe. So you want to ask everyone, could you safely finish the transaction? Is it okay? If everyone says okay, you go ahead and commit. If somebody says no, everybody rolls back. It's a very conservative use, not like majority take over and decide on behalf of the entire group. Okay, is that clear? What the question is, point is? So basically it's a very simple voting protocol. The coordinator is simply going to send a message to everyone saying vote. Okay, everyone votes yes or no to get back the responses. If they are all yeses, it sends back a reply saying commit. If any one response is a no, you send back a response saying abort. That's what two-phase commit is. There are two phases. There's a voting phase and there is the results phase. In the first phase you ask everyone. In the second phase you tell everyone what the results of the election is. Okay? So is that clear what I said? So there are some subtleties to be dealt with here. So you want a scenario where no matter what happens, any process crashes. You want never to be in a scenario where some processes have committed and some have aborted. You always want to guarantee that it's all or nothing. So no matter what happens in the system, you want to basically either everybody has to agree to commit or everybody agrees to abort. Here we are not going to deal with Byzantine faults. That would make the problem harder. We are only dealing with crash faults. If you had Byzantine faults, you would have to go back to our Byzantine general problem. You can't have one coordinator trying to figure that out. But that coordinator may be Byzantine faulty and it will tell you the wrong thing to do. Or it may tell different replicas different things to do, and then the process system will not work at all. Okay. So we'll assume that processes are never going to be erroneous. They can crash. But because they can crash, still bad things can happen. And you want to avoid that. So that's the problem we want to solve. This is a state transition diagram that shows what happens or how the protocol actually executes. Okay, so initially, this is the coordinator, that's each of the replica. Remember that the coordinator is also going to be one of the voters. Just pick of the n replicas, one replica to be a coordinator, so it also does the work and it is acting as the coordinator. Okay. So it basically starts in the init phase and it basically sends a vote message out, saying vote and tell me what each of you want to do. Okay. It will also vote itself. Okay. And it will go into wait state where responses are coming back from all the replicas. Okay. And then it will basically just compare all the responses. If everyone says commit, you are going to send a global commit. Say everybody agrees, go ahead and commit. Okay. If any process has sent back an abort, you send a global abort, saying at least one process says abort, so everybody should abort. That's all that is going to do. Okay, that's the coordinator. Any questions on this? Okay, that's straightforward. Here is the individual processes. Okay, so they have these two phases. So they start from the init and they basically get a vote request. Okay, so then they are going to vote and then go into a ready state saying I am going to now go into this ready state called ready, waiting for the results of the election. Okay. And then when the coordinator basically sends the coordinator sends a global commit, you send an acknowledgement and you actually commit. The coordinator sends a global abort, then you are going to get an acknowledgement and abort. Okay. And there is a direct transition here from init to abort, where if you have voted abort after getting your thing, you don't have to go into ready. Because you know you voted abort, you know the results of the election. Because this is a veto. If I have vetoed, then I don't have to wait to know what the coordinator is going to do. You know what the coordinator is going to do. So you can straight away go and abort. Okay, yes.
What if something changes between the two phases?
What if something
Changes between the two phases? After
only thing that can change is some process actually crashed. Okay, we are going to talk about that. So this looks very trivial, okay, but it's not. Because you have to convince yourself that no matter what process crashes at what point in this protocol, you will never end up in the bad state. Okay? So first take the scenario where the coordinator crashes. Okay, somewhere in between. Okay? So you have to convince yourself that coordinator can crash here, here, here or here. And then what happens if it crashes in any of those states? will any of the processes actually have a problem. Okay, so if the coordinator crashes before the election results have been delivered, then all processes are stuck in ready. Okay, they will basically wait forever, but they won't do anything, but they'll wait forever. This is a disadvantage of the protocol, which says that nothing bad happens, which means you won't have a scenario where some processes have committed and some have aborted. So the safety property is not violated, but nothing good is happening either. You're stuck because you cannot, the coordinator is the one that is going to tell you what to do. The coordinator is crashed, you cannot decide by yourself what to do. So you can ask, why can you not decide for yourself? The coordinator crashed, let's ask each other what you voted and then we can decide. Can that be done?
It is not, these other processes can't guarantee that the coordinator is correct.
No, let's assume it has crashed. Question is not whether the coordinator crashed or not. Let's assume it has crashed. I'm simply asking, saying, if all these processes voted, why are they dependent on the coordinator to tell them a response? If the coordinator crashed, can they just ask each other and decide what to do? They all said, each of them says, okay, we all agreed to commit, let's go ahead and commit. Or they can say, let's play safe, coordinator has crashed, let's simply abort the transaction and move on. Are either of these two okay to do? You see the question, right? You can say, let's play safe, coordinator went down. What's the harm in just aborting? It's always a safe thing, roll back. Would also ask each other, so what did you say? If everybody says commit, you will say let's commit. So in the interest of time, because we have more time, I'm going to tell you what. So it turns out that you as in the rest of the processes cannot decide without the coordinator. Simply because the coordinator is also a replica. It may have voted to do something. You don't know what it voted. Okay, these rest of them may have said, let's play safe and abort. What if they had all voted to commit? The coordinator also voted to commit, and it has decided to commit, but before it could send the messages back, it has committed, so not sent messages back and crashed. So if you say, let's play safe and abort, and the coordinator comes back up, the coordinator has committed, and the rest are aborted. Bad scenario. Or vice versa. Everybody here has agreed to abort, but coordinator is a replica itself. It may have decided to abort, the rest don't know that. Because it's the only one collecting the votes. Votes are not multicast. So it may decide to do the opposite of what everyone else does. So you cannot simply say, let's ignore the coordinator and either play safe and abort. That's not playing safe, because coordinator also votes. And if it actually voted to do the opposite of what you had said and it has agreed to commit, you will actually end up in a bad state. Okay, so you cannot actually, so you can see that it also basically goes and decides whether to abort and commit. So it has reached a decision, and if you reach the opposite decision, then you are going to be stuck. Okay, so this it looks very straightforward, but it's subtle. Okay, so you have to sort of look at all the scenario. And we have only considered the case where the coordinator has crashed. All sorts of bad things can happen if you don't take this protocol into account when some of these parties happen. You can ask, what happens if some process crashes when it's in red? What happens if you receive the results of the vote and you have crashed when you are about to either commit and abort? Then we'll come back and look at that next time. But you have to analyze all of these possibilities and guarantee that always it's all or nothing. No matter what happens, no matter which entity crashes at what point, you will never be in an unsafe state. Okay, it turns out that this protocol is correct. It won't lead you to an unsafe state, but we are trying to reason to ourselves that it's correct, okay, rather than just assuming it is correct. So we'll stop here today. We'll continue this discussion after the exam next week. So For now, we'll just wait.